What did we talk about a couple days ago?
That
I
widespread.
barely remember yesterday.
Our EKG stuff.
Oh, probably just with the group.
Fantastic.
Yeah.
Okay, I want to do something today. I'm gonna put you on the spot pretty soon. But I told you I was going to.
I thought you were.
You thought I was kidding when I say that? I'm not. I won't put you too much on the spot. But I want you to contribute, which I know you always do. But here we go. I want to talk about EKG in a slightly different way, and I want to include all of 12 lead. So I gave you an approach to how to deal with EKG, and I'm going to look at a couple of very specific EKGs. I gave you an approach to how to deal with a single lead, right? We go through a process. What was the process that we went through? You're looking at a single lead. Okay, and I want to take a moment to define those. What do I mean? What is meant by take out the crap?
Something that's
It's not normal. Look at the underlying stuff, not the stuff that's distracting.
Close. Give me more information. What did you say?
I said artifact.
Artifact.
Regularity.
What do I mean by take out the crap? What is crap in this
It
case?
doesn't affect the underlying rhythm.
Okay, yes, yes. Get it to the point though. Get it one step further. What?
Something that doesn't look like the rest.
Say that again.
Something that doesn't look like the rest.
That's what crap is. Something that doesn't look like the rest. And you're all saying what could be crap, right? But it's possible that in one cardiac cycle, y'all understand when I say when a cardiac cycle? What's a cardiac cycle?
B2P.
P to P, good. One cardiac cycle might be total shit. But the next cardiac cycle might be exactly the same thing as the first one. And the third one might be exactly the same as the first two, right? Which means the whole thing is crap. But then nothing is crap. Does that make sense?
Yeah.
When I say take out the crap, I mean look at something that is different than everything else and forget about it. And then look at everything else. Does that make sense? That's important because sometimes crap is not crap. Got it? What was next? What did we do after that? Okay, so and I'm gonna for the purposes of this, I'm gonna combine 2 and 3. So I'll actually make it 2A and 2B. What was it?
Rate.
Rate and rhythm. Rhythm and rate. I kept them as 2 separate steps for you previously. Those really come hand in hand. They go together, and you're establishing them both for the most part at the same time. So rhythm and rate will come next, and with the rhythm, we're trying to find out what?
Regular, irregular.
The regularity of it. It's either regular,
Or irregular.
and if it's irregular,
Is it irregularly irregular?
irregularly irregular, or regularly irregular, which is a whole bunch of what does it mean?
Is there a pattern or not a pattern?
What's that?
Is there a pattern or not a pattern?
Can you establish a pattern out of it or not? Okay? Can you establish a reason why it's irregular that makes it underlyingly regular? Or is it so irregular that you can't establish any pattern or see any reason why it's not? Right? Good. What was after that?
P waves?
Good. P waves. We're looking at P waves for what?
Morphology.
The morphology?
Ratio.
What's that? What's the second thing?
Ratio.
The ratio?
To QRSs. If they're upright.
Interval.
In?
Me too.
Good. You have to always follow it up with what lead you're looking in, so upright lead 2.
Well,
No, say it.
I mean, you say lead 2, but really you're looking that it's, I mean, you could just say you're looking for it to be upside down in AVR, and that's more accurate. because
Absolutely you could.
They should be upright in most leads, except for the leads that it's variable in.
They should be upright in lead 2, and they should be inverted in AVR. That we know hands down. They should also be upright in AVF. That's another place where they should be upright. and they're likely to be upright in lead 1. But the directional travel, in your guys, let's see, which way is right and left for you guys?
Right.
Yeah, okay, right. The directional travel is this direction, right? From upper right to bottom left in the atria. I'm not talking about the ventricles right now. It's the same in the ventricles too, but in the atria. The atria goes that direction.
Will you do it the other way?
You bet. The
That's
atria
your
should go
body.
that direction.
Your
so
body.
lead 2.
Yeah, your body.
Yeah.
The atria is going this way, so lead 2 should be upright. AVR should be inverted. Those two are absolutes. Okay? So good. P wave morphology. You're looking at changes in P wave. You're looking at whatever that P wave looks like. What's next? I'm going to change those to bullet points. The PRI, right? Within its normal limits, understanding what's different about it, if it's wide, if it's long, or if it's short. Then what?
QRS.
And then the QRS, establishing its width, right? Okay. Some books that you read will combine all of these things and just say check for intervals. And it means the same thing. If you read online or read in books or something and it's saying check for your intervals, it's checking your P waves, PRI, and QRSs, right? And I'll go one step further here. This is a new one where I'll actually write in intervals. You already started that process, but there are some other intervals that we're paying attention to. What are those intervals? 3 other intervals that we want to pay attention to. R to R, P to P, and the QT. You've already done some of this in this process, right? Which is why this whole thing is called intervals. But we add that QT to the mix as well. Does that make sense? Okay, QT is ridiculous. The QT interval is ridiculous to deal with. Your QT, this is, you have to be careful about quoting me here because QT is difficult to deal with. The QT should be about 1/3 of the R to R. It should be about 1/3 of the R to R. Okay? Yeah.
For clarification, is the QT from the end of the Q to the beginning of the T or end to end?
What is the QT interval?
Point to the Q to the point to the T.
Do we remember? Do we remember where it starts and ends?
Beginning to beginning.
Isn't it?
Beginning of what?
Beginning of Q, beginning of T.
Okay, so it's the start of the QRS to
The start
End of the T.
end
Oh.
of the T.
It includes, it's not just signal.
So it includes all of the QRS, ST segment, and T wave.
So it's not like the PRA or let's go from the start.
Correct. So it includes all the QRS complex, ST segment, and the T wave. It's really difficult to establish sometimes. It's really hard to tell. So for example, your T wave, your T wave can sometimes do something like this, okay? So you know the T wave is supposed to be asymmetrical, correct? It rises slow and it falls fast. But right around the baseline, we can have funk that happens. That funk is that it's coming back down, and here's my baseline. So my T wave is coming back down and hitting my baseline right there. Does that make sense? Okay. This can be a little bit weird. So some thought process is that that shouldn't be where the end of the T wave is. Some people's thought process is that this is where the T wave should end, and that therefore that's where you should do your calculations. Others are that you should take wherever the T wave finally gets its major bottom slope and continue that to the baseline, and that should be the end of your T wave. But there's a difference in time there, right?
Okay.
And then we have an added problem when you think a U wave comes into play. Because there could be a U wave here that's often tucked right in which case sometimes people will look at that as being the end, which is not, because that's the end of the U wave. Go ahead.
So, how exact do you really need to get that? Because if you have artifacts in there, then
You might have a problem.
you're screwed.
Yeah, it's very difficult to
And
sell.
I want to know how precise all of those measurements should be, like those intervals. I get that QRS is like, if it's wide, but at what point are you like, well, they're you know what I mean? They're
Why does it matter?
confusing, so
It's
it's kind of normal for
approximately
them.
1/3.
Yeah,
And then,
the difference in,
I
the
get
difference
that.
in some of these, in a 10-minute window might be nothing. In a 40-minute window, it might make a big difference. So for example, when we talk about QT and we talk about a long QT interval, one of the ramifications of a long QT interval is the likelihood of an arrhythmia.
because they're going to go into suicides.
Right. And there's many other
RNT.
arrhythmias other than torsades, but the likelihood of that arrhythmia, right? And how can you protect against that likelihood or protect against what they're about to do? But an incorrect measurement, either too short or too long, sets you on an intervention set that might not be accurate or prevents you from recognizing that something terrible might be about to happen based on that information. Am I saying that this is something that you have to measure every single time? No. Those individuals that have a longer transport time need to have that measurement more accurately. But the big problem with the QT interval, the QT interval itself doesn't tell us anything. We have to have what's called a QT corrected interval. Because you can't have, the PR interval is pretty set. We've got a window of PR intervals, right? It's that 0.12 to 0.20. And no matter what, you have massive parasympathetic involvement, you're going to be closer to the 0.20. You have massive sympathetic involvement, you're going to be closer to the 0.12. But you're not going to be less than 0.12, and you're not going to be greater than 0.20. Does that make sense?
Mhm.
That PR interval is reasonably well set. Same thing with the QRS complex. The QRS complex, the depolarization of the QRS complex is pretty set. You're not going to have it grow, and you're not going to have it shrink in a single person. It's fairly set. But what affects the QT interval? What is represented within the QT interval? Physiologically, what's represented within the QT interval?
Depolarization of the
Depolarization
ventricles.
and repolarization. What affects those? What effects can happen to the QT interval?
All kinds of things. Drugs.
I'm talking normal physiology, not pathology.
Oh.
Binary periods.
What about them?
There's absolute and then there's the relative,
Sure.
and if it's in relative refractory, then that just puts itself into a variable of whether or not it will.
True, but for a single person, what can happen to the QT interval? Why is the QT interval not able to have a set number like we have with the PR interval?
Because if we're going to speed up the rate, we're going to shorten the QT interval. Because the
And?
sympathetic system causes it to repolarize faster.
And yes,
And-
if you speed up the rate, you're going to shorten the QT interval. And what else?
There's a period there, I swear.
Sure. If you speed up the rate, you're going to shorten the QT interval. Period. Give me a second sentence.
Dang.
And
It's going to do what? It's going to lengthen the QT interval
Thank you, Andrew.
by quite a bit, right? So it's about 1/3 of the R to R, but the R to R can be drastically different, right? Because the R to R can be,
Oh, yeah.
you can have an R to R interval that's, I don't know, 1 box, or 1.5 boxes, large boxes, or 2 boxes, a rate of 150. So 1/3 of 150
It's way different than 1/3 of
is very different
60.
than 1/3 of 40, right? So there's no way that we can have a range for the QT interval that's reasonable, because if you have a QT interval that's, so what's
They're
1/3 of 40?
constant.
15-ish,
Yeah.
give or take. So we can have a QT interval that goes from 15 to 50. But having a QT interval
50.
of 50 at a rate that should have a QT interval of 15, that's a problem, right? You understand that? So we can't say that the QT interval's normal range is 15 to 50, because it's completely dependent on the heart rate, which means we have to have what's called a corrected QT interval. Now, the corrected QT interval, there's an equation for that. The corrected QT interval is equal to the R to R, is equal to whatever the actual QT interval is divided by the square root
Oh.
of the R to R interval. Now, here's the difference, and this is only this is the most accepted of the different calculations for it.
Oh, so.
But here's the deal. This interval is given to you, it's calculated on the machine already. The monitor will give you that interval. When you look at your 12 leads, the QTC, the corrected QT interval, is given to you. See it there? You're looking at a 12 lead, right?
Yeah, it was,
Did you see it there?
yeah, it's right there.
Excellent.
QTC.
He was lying.
But here's the problem. Here's the problem.
Where's he calculating?
Where does the monitor calculate the end of the T wave? If there's a U wave involved, that's a problem. If there's a biphasic T wave, that's a problem. If there's a weird slope at the end of the T wave, that's a problem. And so you can't ever actually trust the QT intervals produced by the monitor if it actually matters. Meaning, if you have a patient where the QT interval can tell you something really important, and we'll talk later on, we're starting into all the medical stuff. So as we do medical stuff, some of the signs and symptoms that'll be thrown at you would be, this person, you'll see a change in the QT interval. Or this condition has a change in the QT interval, right? In those patients with those conditions, where the QT interval could actually tell you something important, you can't just rely on a monitor. And cardiologists would never rely on the monitor. They have to actually calculate it by hand, because you have to look at the EKG and actually establish where that T wave really is ending, not where the monitor says the T wave ends, because there's so much fluctuation with what happens at the tail end of that T wave that it can be difficult to tell. Does that make sense? Okay, so am I asking you to calculate your QT intervals on all of these 12 leads? No, I'm not. Am I saying that you can't ever look at the QTC on a monitor and trust it? I'm not saying that either, right? But if you have a patient where the QT interval is a key component of the signs and symptoms, that's the moment that you go, all right, I'll get a general idea from my monitor as to what it might be, but I might need to calculate that myself to find out really if that's happening in fact. Does that make sense? Okay. So those are all the intervals. Okay.
So Annalise, what does the QTC say on there? What's the actual version?
You don't want this one, this leaves.
Should be in milliseconds. Yep.
The QT interval is 462 milliseconds, the QTC is 508.
So if you have a,
Graphing
if you're trying to calculate, you have a patient has a symptom that leads us down picking for the QT interval. I don't know what my question is. I'm sorry.
I don't know which questions you had. Go back to it. Okay. Okay, so there we go on the intervals. And then, what's next? I would argue that, I say put the crap back in. I want to put another step in here before that.
T-wave?
What, yeah. Give your rhythm identification.
Interpretation.
Oh, where's the interpretation?
Give your rhythm interpretation, right? And then after you give your rhythm interpretation, what do you do?
Identify the trap.
Okay. Go back to identify the crap. Does that make sense? Questions on that process? It's a process that we've been doing since day one, right? All right, I want to add and change just a little bit in here on what we're talking about. Because now we're looking at 12 leads, right? And this isn't going to be different. We're just going to add to some characteristics here when we look at a 12 lead. So what are some various things that we look at on a 12 lead to find out if this patient is normal or abnormal? What are different things that we try to look at?
Look at AVF and look at lead 1 to determine our axis.
Okay, so we look at axis. What else do we look at?
AVR.
Why do we look at AVR?
It's negative if it's normal.
When is it negative?
When it's normal.
When it's normal. How often is it negative when it's normal?
All the time.
All the time. Right? AVR is directly opposite the flow of electrical activity under all normal circumstances. Right? There aren't any normal circumstances where AVR would be positive. So we get a picture of AVR. What else might we look at?
I mean, hopefully lead 2 is mostly positive. There's no ST elevation and any of the.
Is lead 2 mostly positive for the QRS complex?
Not all.
Depending on the axis, but I would say most of the time,
What's the normal axis? Degrees wise, what's the normal axis? What is normal?
Negative
90.
30
Oh,
to,
Zero.
negative 30 to 90.
Negative 30 down to 90, right?
Or like
In fact,
100.
negative 30 down to 110. Of which lead 2 is in the middle of. But is lead 2 always positive for the QRS?
No.
It can be pretty biphasic too, right?
Most of the
Granted, it's usually not negative, so that's good, right? So it's okay there. What is it for the P wave though?
positive.
That's always positive. It's always upright. I should also mention, by the way, the QT interval is almost always measured off of either lead 2 or V5. Lead 2 and V5, and that's because those two show you the best version of the T wave. The T wave. And leads like lead 3 are never looked at for the QT interval because the T wave can never be trusted in lead 3 in terms of exactly where it is. So we'll come back to QT interval later, but I throw that out. Okay, so yeah, we kind of look at some leads to see what is actually normal. Amanda, you mentioned something else.
Z-axis.
What's the z-axis?
All the V leads, precordial leads.
Okay, I can't stress this enough. One of the things you guys have to be able to do, and you have to practice this until you can do it, you have to know exactly where the leads are supposed to be placed. I think we made that pretty apparent a couple of weeks ago, right? Not only do you have to know exactly where the leads have to be placed on the person, but you have to know what that translates into in terms of its picture of the heart. That is critical, right? So when Amanda mentions the z-axis is talking about, so we have the x-axis, right? We're just talking about graphing now. We have the x-axis, we have the y-axis. What's the z-axis? This is the z-axis. Does that make sense? It's just to put a name to it. So when we look at that, the z-axis is talking about V1 through V6.
Oh, right in the middle.
Right.
V1 through V6 is what we're looking at now, right? You have to be able to translate where the camera is, what direction it's taking the picture of, and then what it should look like. So where is V1 located? On the heart, not on your body. Meaning where is the camera sitting for the heart?
Just right on the right age.
Up here?
No.
Down.
Could be right.
Right there.
Yeah.
Okay, that's V1. That's where V1 looks, and the camera is taking a picture in what direction?
From the middle out.
Towards the middle of the heart. So the picture is this direction. So V1 is looking at what anatomical portion of the heart?
Right.
Atrium.
The right
Right.
ventricle. Right atrium is up here. We're down here on the ventricles. Right? So it takes a picture of the right ventricle primarily. Does that make sense? The majority of the electrical activity in the heart is happening in what part of the heart? The left ventricle. And it is happening in what general direction most of the time?
Away from V1. From the top down.
I'm sorry, wait, can you like back up?
I can.
V1 is looking at your right ventricle?
Yes. That's the whole point of V1. How is the heart situated in my body? How is the heart situated?
Looking for
Like this?
It's like this. And what else?
Slightly rotating.
Rotated to what is anterior?
Right ventricle.
The right ventricle is anterior. The left ventricle is posterior. It is not, the heart is not situated where the septum between the right and left ventricles is center mass. It is rotated so that the right ventricle is anatomically in front.
Yeah, but if V
And the fourth
one
intercostal
is
space
right
falls
here,
where?
shouldn't that look like directly through?
V1 is where? Where is V1 on your person?
Fourth intercostal
Fourth
space.
The fourth
intercostal
intercostal
space.
space, which is at the ventricular level. Your atria is above your fourth intercostal space. You're looking right at the ventricles. And you travel it across the ventricles. That's the whole point of the 12 lead. Why does the 12 lead need to be in the fourth intercostal space?
To look right at the ventricle.
So you get a picture of the ventricles, which is what it's supposed to get a picture of. That's the whole reason why we are so insistent that you don't just jam a sticker on their chest. If you get it too high, you're not getting a picture of the ventricle and you're getting a different angle of the electrical activity. That's why it's so important that you find that fourth intercostal space, because in 80% of the 7 billion people on this planet, the ventricles are in the fourth and fifth intercostal spaces. That's why we have it there. So, V1, which is there,
Then why do you look at V1 and get a good picture of your P wave?
because you can get a good picture of your P-wave.
I am feeling lied to right now.
Yeah, I just remember we had this talk about like,
You're gonna get a
Looking
picture of
at
your
the-
atria.
Yeah, you will. You will get some picture of the atria too. And the atria fires when compared to the ventricles.
before.
So it's the only thing that's happening. So all of your leads are going to show you something with the atria.
Okay, I'll take that.
I'm not gonna take that, what the heck?
You what?
What's lead 2 looking at?
What is lead 2 looking at?
I asked you first.
Does lead 2 see the atria?
Yeah.
Because why?
Because it's looking up at it.
Because nothing else is happening at that
Right.
time. All it can see is the atria. All of the ventricle stuff is just nothing. It's a window because the only electrical activity is happening is in the atria, right? What would we see in lead 2? What atrial activity would we see in lead 2?
I'm not asking about lead 2, I'm asking V2.
You just, I haven't got to V2 yet.
Well,
Oh, you
I
said-
meant-
But this will
I
answer
meant
that
to
question
say
too.
V2.
You said lead
what will happen in lead 2s? What will we see in the atria from lead 2 if the atria and the ventricles fired at the same time?
QRS.
Nothing.
Nothing, because the atria would be what?
Bigger, more electrical activity to overshadow the,
Yeah,
The
it would be
atria.
completely hidden. And the
But you're
only
not
reason,
seeing nothing, you're seeing the QRS.
that wasn't my question. I didn't say, what did you see? I said, what of the atria would you see?
I wasn't listening.
And that's why we don't see atrial repolarization.
Which is why we don't see atrial repolarization, because it's happening during the QRS most of the time.
why
Okay.
don't we see
Let's go back to B1. So the heart is anatomically, it's shifted like this, and it's shifted like this, so that the right atria is in the anterior view, right? And V1 is looking directly at the right atria. And yes, it also sees the
No, it's
septum.
ventricle, yo.
Sorry.
God dang it.
Thank you. The ventricle. See, you caught me. That's good. It's looking right at the right ventricle. You see the right side
Nice.
of the septum as well, right? And you see something that's happening in the left ventricle because there's so much electrical activity that's happening there, but that's important for us to figure out what that is in just a minute. So the V1 is looking is looking directly at the right ventricle. Does that make sense? The two ventricles are depolarizing simultaneously. Yes? Do we agree with that? Most of the time, under normal circumstances. The septum is going to fire first. So as the signal starts to come down, the septum gets the signal first. The right ventricle gets that signal just a skosh before the left side, but then really both ventricles are firing together after that. So in V1, no, I need to go back to the question that I asked before we got off on that. So my question was, in the left ventricle, what is the direction of electrical travel in the left ventricle?
Or lead 2.
What is it?
Anterior to posterior.
Anterior to posterior and superior to inferior and endocardium to epicardium, which makes it go, so that's overall. Endocardium to epicardium is always there. So it's going anterior, so keep what Andrew said in the forefront of your mind, because that's critical to understand. Then it's going anterior to posterior most of the time. It's going superior to inferior most of the time. And can you use directional terms to say that? Give me directional terms based on your one side of your body to the other.
Middle,
Right to left.
medial.
It's going right to left, superior to inferior, anterior to posterior. Is the primary electrical activity of the left ventricle. Because it's three-dimensional. Right? The high school version of electrical activity in the left ventricle is top right to bottom left. Right? The college version is top right to bottom left, front to back, top to bottom. Right? Right to left. This direction. So when we're situated like this, right, the anterior of the left ventricle is more on the left side. So the anterior of the left ventricle goes that direction. Do you understand that? Because it's shifted. So the anterior portion of the left ventricle
Body, right?
in my body is here, so it's going that direction. Do you understand that? The heart, there's my septum. So anterior would be here for the left and here for the right, but the heart is shifted like this. So the anterior portion of the left ventricle goes that direction, not that direction. You have to remove your you know what anterior means, right? Generally speaking. But now you have to think of it in context. And the heart is shifted. So anterior is that direction. Does that make sense? For the heart.
Not your body.
Not your body, for the heart. Okay, so here's my V1.
So can I
Yeah.
make an animal?
An animal.
An animal?
I don't know.
Anatomical clarification that the most anterior portion of the heart is the septum, yet even though it's shifted, the heart is shifted in this direction, it's still considered the most anterior, even though it's pointing off that direction. It's not pointing forward. So
The left ventricle is not pointing forward, that's correct.
But the septum is the most, even though the left ventricle is anterior, anterior is forward, but it's more laterally,
Yes.
but it's still referred to as the most anterior portion of the heart, even though.
No, it is referred to as the anterior portion of the left ventricle.
I'm sorry, that's what I meant, the left ventricle.
Not the heart.
Even though it's pointed
Yeah,
laterally.
correct.
Okay.
Because we're using the septum, the power is the B,
As in the-
probably Da Vinci, right? When he chopped up bodies and looked at the heart, and took the heart out and looked at the heart, he took the heart out and saw a septum there and went, oh, right, left, at the septum. But when you shove it back in the body, it turns. But telling me that this is the midpoint, the middle of the right ventricle being the midpoint of the heart is really inconvenient for a whole lot of reasons. Right? So, the anterior of the heart is that way. The lateral of the heart is that way. The posterior of the heart is that way. And there's a whole bunch of muscle mass going on in the posterior portion of our heart.
We're not saying full lateral, like, we could do a one right, sorry, other side, one like farther back, and you'd still be.
What we do, we change it from a 12 lead to a 15 lead, and we get to see the rest of it. Which
But
is
one of these leads still would still be considered a lateral lead.
yeah,
and then
V7 is showing you some of the lateral part of the heart as it gets into the posterior. That's correct. Right? Okay, so here's V1, right? So, V1 is here. My electrical activity in my heart is going this way, that way, and a whole hell of a lot that way. Because that's where the muscle mass of the heart is, of the left ventricle. Does that make sense? So from the right, from the V1 standpoint, from that camera, the majority of the heart's electrical activity is traveling in what direction to that camera?
Away from it.
away.
Away from it. Now, the septum depolarizes first, and that septum depolarizes this way. In the left ventricle, it goes from where to where? In all of the heart, it depolarizes from where to where?
Kind of very in that.
So the septum, here's my right ventricle. This is my left ventricle. Right? The depolarization is traveling this direction. Yes?
Yes.
And I'm just two-dimensional because I can't draw arrows that way because I'm not good enough to do that. Right? So this area depolarizes first. That area depolarizing first is what related to V1?
Coming towards it.
It's coming towards it. So therefore that's what?
Positive.
How much muscle mass is the septum?
Comparatively
Not a
not.
lot. So what we see in V1 is a little tiny R wave because it's the first thing to depolarize. What else is depolarizing at the same time?
Ventricles.
Nothing! Because it's what?
First.
It's first. So there's nothing else going on. So therefore that's all it can see. So therefore it's positive. But then what happens?
Everything else fires.
Everything else fires, which is majority of the time going in what direction to V1?
Away.
Away. So you see a big giant S wave in V1. Does that make sense?
So does it just kind of slowly become more, for us, just slowly
I don't
becomes
know,
more
let's find out.
positive as you?
Here's my V2. My V2 is also looking at the septum and everything else, yes? What is the primary directional flow happening with V2? What fires first? And what is the directional flow of the septum compared to V2? It goes towards it. So in V2, it's primarily going towards it, yes? So we see an R wave. And then what happens to the majority of the flow? It starts going away. Now, V2 does show you a little bit of the anterior portion of the left ventricle. And the anterior portion of the left ventricle has directional flow that's going where? Towards it. So some of it is going towards, more of it's going towards V2 than was going towards V1. And a whole lot is going away. Now when you add that all into the mix, you don't actually see more, a greater upward motion, but you see a smaller downward motion because we've got more forward motion mixed in. So with V2, I see a very, very negative V2, but not as negative as V1. Does that make sense? Now I'm at V3. V3 is here. V3 sees what?
Left ventricle.
All left ventricle. It's looking at the anterior portion of the left ventricle. The anterior portion of the left ventricle is firing in what direction to V3?
A little towards.
Directly towards it. And what's happening, or close to being towards it? We do see a skosh of that right ventricle. You don't see, I don't want you to think that V3 shows you the right ventricle. But because that right ventricle is firing right near it, that electrical activity is pretty heavy on V3 comparatively to the other leads. So we have to enter that mix, which is going that direction. And then we have a whole lot that's going this way. So V3 shows you a pretty decent positive wave because of all that anterior stuff that it's seeing. But it does see a little of everything else, and that's going all directly away from it. So V3 also tends to be negative, but not nearly negative as V1 and V2, and a whole lot of positivity also because it sees a lot of that anterior portion, which is going directly at it. Does that make sense?
Is that just added on top of the septum?
Yeah, so the septum, this very, very brief portion of it is going to be
The
that
septum,
septum.
and then it just keeps going
And then
up,
just, yeah.
and then down.
Yep.
So would you say that V3 is the most biphasic,
No.
I would not
limb
necessarily
lead?
say that.
or IV axis?
I wouldn't say that. So V4 is over here. Now what is V4 looking at?
Left ventricle.
Yeah, all left ventricle. We call it what kind of a lead? An anterior lead. So it sees a whole big portion of the anterior, and it starts to see a bit of what? The lateral. So it's seeing all this stuff going this way and all this stuff going this way, and the stuff that's going back from it is what? Is getting more what to V4? More perpendicular. So the stuff that's going posterior is getting more perpendicular, which means how much negativity is it adding to V4? Not a whole lot. The right ventricle is the primary negative aspect of V4. The posterior stuff is more biphasic to it. It sees a lot of that anterior and a lot of that lateral. So V4 is quite positive. It does have still a distinct amount of negativity to it too, because there is stuff that's going on all around it. But because a lot of that is biphasic, it's seen as less on the negative side. So something very special happens between V3 and V4. What? A transition. The transition is almost always between V3 to V4, where we go from negative to positive. Okay? Now, we're at V5. V5 is what lead? What kind of a lead? We call it a lateral lead. What's it looking at?
Left ventricle.
The lateral left ventricle and some of the anterior and some of the posterior. But the majority of the electrical activity is doing what related to V5?
Towards it.
It's going right towards it. It's either going towards it or biphasic to it. Almost none of the left ventricle firing is going away from V5. It is either going towards it or biphasic to it. Nothing's going away. Now the only thing going away is the right ventricle, which is deep into the mix of everything else that's happening on the left side, and it sees so much left muscle mass. And you remember that the V leads, where's the negative for the V leads?
In the middle of the heart.
In the middle of the heart, Wilson's terminal, which is the middle of the heart, which means it does see what's happening on the right side, but not as well as, say, lead 1. So what we see with V5 is we see a big positive wave and almost no negative wave to it at all. Right?
Why isn't the septum slightly negative in V5 and V6?
The septum is so slight that it is so tiny that it gets all completely mixed into all the average of everything else that you see.
But if it goes
And sometimes
first,
you can see a little bit of a Q wave to begin that.
would you see it negative then?
You would see a negative Q wave. And sometimes you do see a little bit of a Q wave there. The problem is that with V5 and V6, because it goes to Wilson's terminal, it starts not seeing clearly what's happening closer to the right side. So for example, you're more likely to see a small little Q wave in lead 1 than you would in V6. Because lead 1 has the negative all the way on the other side of the heart. So it's a deeper lead to be able to see what's going on, right?